Hello YouTube! So today we're going to be talking about 2D collisions. This is a little bit weird for the Physics C thing because what I've been doing is relying on the AP Physics 1 videos to sort of compensate because a lot of them are very similar, and then we're mostly going to be talking about the differences between the AP Physics C stuff and the AP Physics 1 stuff. So if you want the AP Physics 1 stuff, that'll give you a pretty good supplement of everything leading up to this. And this is sort of, okay, well, once you understand the stuff from AP Physics 1, or more accurately, a little bit in the middle of it, how do you do the parts that are specifically Physics C? So, ideally, end of the day, you should be able to have everything you need to model motion when an object collides with another object in 2 dimensions. Something that we won't be doing from that is figuring out which angle spherical objects will bounce off of each other when they collide. That's something that occasionally college courses can include, but is definitely above the scope of AP Physics C. But aside from that, that's sort of, we're going to cover all the basics. So in order to do that, hopefully you should be able to describe what happens when something collides with a wall. So in particular, be able to talk about which component of the velocity will change and which one won't. And then also use systems of equations to model the direction of each direction of motion, so each component of motion when you're doing a collision, and then use that to actually solve things out. We'll start with the walls. So in particular, when an object hits a wall, specifically elastically, which will make more sense later if you haven't learned about elastic collisions yet, the component of the velocity that's normal to the wall is going to flip. And that is a statement that makes a lot more sense with the picture. So, if the thing is coming at an angle like this, then there's going to be 2 components to its velocity vector. So if this is its velocity vector and the white is its displacement vector, then in red we've got our x component in this case, and let's go with the gray, y component. And our x component when we hit the wall is perpendicular to the wall. And so because the x component is normal to the wall, once we hit the wall, our gray component, our y component, isn't going to change at all because that part's parallel. And our x component is going to flip directions. It actually means that I put the gray one in not quite the right spot to make it more visible. So we've got our y component, and that part will be the same. And then we've got our x component, and instead of going to the left, our x component is going to go to the right. And the thing that's kind of weird about that, but makes some level of sense, is that our magnitude for our momentum of the object hasn't actually changed when we hit the wall. So if we look at the blue part, because the components are the same length as each other, the diagonal has to be the same length as well, because similar triangles. Just as which also actually has some implications for the angle. Let's start there. So when it leaves, it's going to be coming off on this dotted line. And the reason why that looks so significant is because this angle here will be the same as this angle here. And that should make some level of sense if you look at the similar triangles. Inside parallel axis theorem means that these 2 angles are also the same. And so because the diagonal is the same and the opposite side length is the same and the adjacent side length is the same, by any trig function you like, it's going to have to be the same angle. And in particular, there's another angle that's always going to be the same, which is the angle from the normal line on the wall, so the line perpendicular to the wall, to the velocity vector. So these 2 angles here are going to be the same. And that can be pretty useful for some problem solving, because generally speaking, anytime you can get some symmetry involved, it's sort of either a quick shortcut or a necessary problem solving tool. The comment about the object being spinning that's on the slide is in particular that if you have something that's spinning, the fact that it's moving against the wall means the small grooves in the object can generate friction with the wall, because normal force is what's causing the thing to turn if it's not spinning. You're not trying to slide against the wall in an appreciable amount, so you're not going to be able to get an appreciable amount of... you could potentially get some, but you wouldn't get an appreciable amount of y momentum in this case, because you don't have any forces going in the y direction. But if you have the thing spinning, then because it's moving against the wall in the y direction, then you're able to get friction going in the y direction to create a change in momentum in the y direction. And so that's why if you've ever seen like a spinning tennis ball or a spinning lacrosse ball or something that hits the ground and bounces so weird, that's why it's bouncing so weird, is because what your brain is expecting is what'll happen if it doesn't spin, which is in particular that it bounces off such that just the y component flips, minus some energy loss. But when it's spinning, it's able to have also the x component flip, and that's what makes it weird. Although I guess in that case it'd be 3D, so it'd be the z component, but we can put our axes wherever we want, so it doesn't super matter. All right, so as an example, let's say we've got a pool player who wants to hit a pool ball that's 0.12 meters away from the cue ball, parallel to the wall. How fast did they hit the cue if the cue collides with the ball 0.2 seconds later and the ball is 0.08 meters away? So, oops, let me get, there we go. Let me get this in the right mode for copying down the problem. So we've got our pool cue, and we need to figure out how to hit that. Oh my gosh. Sorry, I just realized that I forgot to specify something in this problem. They want to hit a bank shot, so they want to hit the wall and then hit the pool cue. They don't want to just hit the pool cue. This problem is 12 divided by 0.2, if that's not the case, because you're just... Anyway, sorry, so that's highly irrelevant. So there's our picture. We know that this distance is 0.08 and this distance is 0.12. And we know that our time is 0.2 seconds. All right, well, with that out of the way, let's dive in. So in particular, one of the big things here is that the angle of incidence is going to be the same as the angle of reflection. And that lets you do some interesting things with the geometry. In particular, it means that if I'm drawing this triangle here between the place where the ball hits and the two pool cues, that triangle is going to be similar to the displacement triangles, or is going to just be the displacement triangles, but it's also going to be similar to the velocity triangles, and the two sides of the triangle are going to be two isosceles triangles. Sorry, it's going to be an isosceles triangle. The two halves we can then break up into right triangles with the same diagonal lengths, which is helpful because that means that this component of the triangle is going to be 0.08 meters. This component of the triangle is going to be half of that total of 0.12, so 0.06. And oh no, I just realized that we can solve this very quickly without using any momentum, just as a 2D motion problem, and honestly that's probably the way to do it. And I shouldn't be using any momentum anyway. We can use those similar triangles to then figure out our distances. In particular, this is a 3, 4, 5 triangle, and so if it's 3, 8, then, or sorry, 6, 8, then this one would be 0.1, and this one would also be 0.1. So what we can do is say that our velocity is going to be equal to our displacement divided by our time, because we'll travel at about a constant speed throughout, because when we collide with the wall, our speed doesn't change, just our direction changes. And so we'll wind up with, specifically because it was an elastic collision and we didn't lose any kinetic energy and the wall didn't start moving. Our displacement we just figured out was 0.2 in total. Our time is 0.2. And so our pool ball is going a cool 2 miles per hour, which I didn't make this problem particularly well as far as the specific numbers. But this is sort of a rough way that you can wind up using your two-dimensional motion in this case, in particular that it flips when it hits the wall. And we might have literally already covered this during kinematics, but now you sort of know why, which is that during an elastic collision, the kinetic energy is conserved, so the total speed stays the same, and in particular, you're only getting force in the direction perpendicular to the wall, and so the only thing that you can have happen is have your perpendicular component change. The only way to keep the vector the same when one of the components isn't changing and have it stay the same size is to just take the other component and flip it around, because if you did anything else, you'd either get a larger triangle or a smaller triangle. So there's obviously more you can do with this for problems, but this is sort of the basic gist. You use the fact that the angle is staying the same, you use that to do some fun little geometry tricks. That's the problem. All right, so what if we actually have a collision in 2 dimensions that we have to model with momentum? Well, if we're doing that, the momentum is conserved in each direction, both separately and together. And so what I mean by that is that the x components of the momentum plus the x components of the momentum will need to equal the x components of the momentum after the collision plus the x components after the collision for every object. But also that that'll happen to the y direction, and also that that'll happen in the overarching just momentum direction. Now, you don't often set up a actually, I'm not sure that last bit is true, which highlights my professionalism. So, but certainly the components are constant, and oh no, because the components are constant and the diagonal has to be constant as well, Jesus. So, yes, so you don't normally do a magnitude of the vector equation. You theoretically should be able to, but normally the way that the problems are set up, it's more useful to do an x component one and a y component one separately, because you'll be given things with angles, and that makes it easier to have an actual system of equations that you can solve, because that lets you solve for 2 variables instead of 1 in a scenario where you'd normally only be able to have the 1, because you'd normally only have the 1 equation. This isn't something that we're going to really model with this last bullet point here, but a lot of times what you can do is, if you don't have it already set up for the problem so that there is a vector that you don't have to worry about components for, you can just use it as the vector. It helps a lot to rotate the reference frames, much like with hills, so that as many of the vectors as possible don't have components, and that'll make your math a lot easier. But again, the way I've set up the problems that we'll be doing, it's kind of already done for us. So as a second example, and this one is a little bit easier than the other, we've got a ball with a velocity of +4 I hat meters per second. I did unit lists for this for some reason. When it hits another identical ball that's at rest. What's the velocity of the ball that was originally at rest after the collision if the ball that was moving now has a velocity of -2 I hat plus 3 j hat? So again, just copying this one down. We've got a situation where this ball is coming in and it's going to the right with a velocity of 4 meters per second. That's the velocity for the first one at the beginning. And our velocity for our second one at the beginning was 0. After the collision, we've got a situation where the first one is now going to the left, component of minus 2 meters per second, so that is V1 final in the x direction, and V1 final in the y direction is equal to plus 3 meters per second. For the other ball, we don't know which way it's going. But what we can do is just conceptually take a quick look at it to figure out which way to draw the arrow. So this ball got momentum going to the left in a pretty sizable chunk because it used to be going to the right and now it's going to the left. It also got some momentum going up because it used to be going straight to the right and now it's going up. That means that our other ball is going to need to get momentum going down and momentum going to the right. And so if we want to solve this out, we can use an honestly pretty gratuitous equation for this situation and set up our x direction such that m1v1x initial in the x direction plus m2v2 initial in the y direction is equal to m1v1 final in the x direction plus m2v2 final in the x direction. We'll do the same thing for the y. m1v1 initial y plus m2v2 initial y equals m1v1 final x plus y plus m2v2 final y. Worst part of momentum is definitely just keeping your subscripts straight. Yep. So from there, we know that this is 0, we know that this is 0, and that makes these equations a little bit easier. In our x direction, our only variable here actually is the mass, but because all of the masses are equal to each other, I can just write these in as m instead of writing them in as m1, m2. And our only variable from there, we know the initial velocity and final velocity of the first object, so it's the final velocity in the x direction for the other object. So we can do m times v1 initial x equals m times v1 final x plus m times v2 final x. And thankfully, if we divide each side by m, the mass drops, so I can go ahead and get rid of all those masses. And that means that nice and easy, all we have to do to solve this sucker is get our given over to the other side. So minus v1fx, v1fx, and we wind up with v1 initial in the x direction minus v1 final in the x direction is equal to v2 final in the x direction. We know that v1 initial and v1 final are 4 and -2 respectively, which gives us out positive 6 as our answer in the x direction. We could do the same thing in the y direction, but hopefully, oh no, I did the thing where I left it on the copying mode. Oh well. If we look in the y direction, the math's going to be the same. We're going to cancel out the masses. The initial velocity in the y direction is 0 for the second one. We're going to subtract it off. Same algebra, same setup, and so we'll get the same result just with y's instead of x's. The times where they look different from each other is like if one of them has a 0 in the x direction, but not a 0 in the y direction, and something like that. So in particular, we're going to get v1 initial in the y direction minus v1 final in the y direction equals v2 final in the y direction. Our initial is 0, our final is 3. 0 minus 3 gives us -3. So -3 direction meters per second is our component for our velocity in the y direction. So v2 final is going to be plus 6 meters per second I hat plus negative 3 meters per second j hat. Okay, so if you have something where something's at rest, they don't stick together, you're given some stuff at the end, it's just as easy as the momentum problems where you've got a situation like that. They can get a little harder where you have to actually use a system of equations if you start getting situations where you're given angles, and especially if they don't have the same mass as each other, or you start having to have things like stick together or something like that. So let's do one of those and then call it. All right, so 2 cars collide and stick together, 1,000 kilogram car and a truck of unknown mass. The car was originally going 20 meters per second at 37 degrees north of east, and the truck was going 4 meters per second north. After the collision, they slide at an angle of 68.2 degrees north of east. Absolutely no reason. There's a reason. What was the mass of the truck, and how fast did they move after the collision? So, getting this one copied down, and I promise I won't accidentally leave it on the wrong side for the whole time, this one. So we've got our first object that's going in this direction, 37 degrees, and has a magnitude of 20 meters per second, and a mass that we know. We have our second object, which is coming in hot at 4 meters per second. I don't know why one of them is going 40 and one of them is going 8, but here we are. Where we don't know M2. And then for our after, we've got one stuck together object sliding off at 68.2 degrees north of east, and we don't know the velocity at the end. All right, so first off, we're asked to find the mass of the truck, and then we're asked to find the velocity. 2 variables. If we set up the x direction and y direction, we'll get 2 equations and we can solve it out. So do that. X direction, we've got m1 v1 initial plus m2 v2 initial is equal to our combined mass times their velocity at the end, because they're stuck together at the end. In our y direction, it'll be pretty similar, but as always, I forgot the subscripts, but with x's, y's instead of the x's that I just added. So m2 v2 initial in the y direction equals m1 plus m2 times v final in the y direction. At this point, specifically because I've got angles, I'm going to start representing these things in terms of their components. If we're looking here and here, let me make that a little bigger actually. And let's make this one a little bigger too, so we can do something similar. Then our v1 initial x is going to equal v1 initial times the cosine of the angle, and y is going to be the same, but with the sine of the angle. Oops, no x there, sine theta. And we can do a similar thing with our vf. This is vi1 initial, this is vx. The fx is going to be equal to vf cosine theta, and vfy is going to be equal to vf times the sine of theta. Great. So equation time. In the x direction, when we plug stuff in, we'll get our m1, which we know, times v1 initial times the cosine of our angle, plus 0, because our truck was not moving in the x direction. And that'll equal our combined mass times our final velocity times the cosine of, I'm actually going to do theta 1, theta 2 real quick. Maybe theta 1 and theta final. Cosine theta final. Just so I remember to plug in the right ones in the right spots and don't accidentally turn them into trig identities when I can't. Because I definitely would have done that. And so what I can do here is, if I'm trying to solve for mass, the only way I can do that is if I've got things solved in terms of VF, our other variable. So I can plug that into my other equation for my system of equations. I know I'm going to need to do that, so before I've even got the other equation ready, I can just go ahead and set up for it, specifically because the math for that's very easy. We're just going to divide by the two things that are multiplied by VF, and we're done. So divide by m1 plus m2 times the cosine of our second angle, and we've got VF isolated. So VF is equal to m1 over m1 plus m2 times V1 initial times the angle ratio. So this is something a little bit interesting, which is that our final velocity is going to be dependent both on our mass ratio and on our angle ratio. And so that probably means there's a fairly existent relationship between the angle that they slide off at when they hit each other and the momentum ratios of the two objects at the beginning. Or the objects at the beginning and the objects at the end. Over in the y direction, we're now all ready to plug that in if we go ahead and set it up as m1 v1 initial times the sine of theta 1 plus m2 v2 initial, which will equal their combined mass times their final velocity times the sine of our final angle. Going ahead and plugging in, we'll get a very similar equation. Or it's m1 v1 initial sine theta 1 times plus m2 times v2 initial times m1 plus m2 times v final, which is m1 over m1 plus m2 times v1 initial times the cosine of theta 1 divided by the cosine of theta final times the sine of theta final from our original equation. So all that junk is plugged in for VF. Sweet. So at this point, we just have to solve for m2. Now, thankfully, the m1 plus m2's drop because we've got them on top and bottom. And so we don't have to worry about the total mass messing that up. Nice little thing we can also do to combine is that these two do actually turn into a trig identity of tangent theta f, although that's actually cotangent. No, opposite over adjacent side, that's tangent. Theta f, so we don't have to do quite as much writing. And at this point, we're looking for m2. Our only variable on, there's only one place where m2 shows up, so we just have to subtract off m1 v1 initial sine theta 1 minus m1 v1 initial sign theta 1. And that'll give us m2 v2 initial is equal to m1 v1 initial cosine theta 1 times the tangent of our final angle minus m1 v1 initial sine theta 1. So being real careful here, this is one of the spaces where being really neat, being really careful with your subscripts, labeling everything out is really helpful because there's just so many letters that look so similar. Our only variable left on this point on the left, our only constant left on given, our only non-variable left is v2 initial. So divide that by each side, and we're left with m2. Plugging in our numbers, I'm running out of space, so I'm getting a little sloppy here. By not rewriting it as another line. We've got m1 is 1,000. We've got v1 initial is, I wrote it down, so I would have it 20 times the cosine of 37 degrees, which it's a 3, 4, 5 triangle, and that's the long one, so those are 16, times tangent theta final, which, because I picked the angle, I know to be 0.4. And I'm just double checking that it's 0.4 instead of 4. Let me do a quick check on that, friend. Whoops. It is not. It is 2.5. Yeah, 10 over 4. Great, we're good. I just flipped the... Which one was the denominator and which was the numerator? Minus m1, which is 1,000 again, times our other component, which was going to be 16 and 12. And we're dividing that by v2 initial, which was 4. Whew. So we've got 2.5 times 2,000. You know, this is why we have calculators. So 1,000 times 16 times 2.5 minus 1,000 times 12,000. I feel like I say that about calculators, and then every single time I feel really silly about how, like, as I'm writing it out, I could have probably just figured it out. But that gives us 7,000 as our answer. Am I fully committed to, or prepared to believe that I got the math wrong a little bit somewhere along the way? Oh yeah, absolutely. But the concepts should all be spot on. Classic excuse, I know, but I'm giving it. In the y direction, if we bring that back to the x direction, oh, there's my alarm telling me I'm supposed to wake up. Silly alarm. But please stop though. Okay, cool. In the x direction, we can come back and plug this 0.78 in to what we had solved for VF. Because remember, VF equals M1 divided by their total mass times V1 initial times the cosine of theta 1 divided by the cosine of theta final. So that's going to be 1,000 divided by 8,000 times 20 times cosine, so that's going to be 16 divided by our cosine theta final, which is going to be the cosine of 68.2. So, once again, relying on our calculator, 1 divided by 8, ooh, I did not have numlock on before I tried that. 1 divided by 8, no, please, clear. 1 divided by 8 times 16 times, oh, not times, divided by cosine of 68.2, which gives us a final velocity of 5.4 meters per second. Which I am fairly confident means I did something slightly wrong for the numbers, but again, the concepts are all there. It's basically just you're doing momentum problems, you're doing it twice, once in the x, once in the y, and because there's components now, there's that added layer of you have to set up your components and you have to be more careful than I probably was about the angles. In my head, I'm fairly confident that the way I designed the problem, the final answer should be such that the y component is 10 meters per second and the x component is 4 meters per second. And that didn't happen. But it's because math is hard, and I made it 4 meters per second instead of 6 meters per second for the truck's speed, so I think we're fine. Or I should have made the truck's speed 5 meters per second. I should have made the truck speed 5 meters per second if I wanted that to happen, I believe. Anyway, that's neither here nor there. What's here nor there is I hope you have a great whatever time frame you're on. Goodbye, YouTube.